Perfect. So I am Mahin Ahmed, and I'm part of the Silicon Austria Labs here in Linz. And I will be giving the talk about time synchronization aspects in TSN and 5G TSN networks. Let's look at what the topics I will be covering today. So I will first motivate for the importance of time synchronization. I will also give some basics of time synchronization, and then we will go in depth into the time synchronization mechanisms for time-sensitive networking, particularly the generalized precision time protocol. I will end the talk with a short detail on 5G TSN as it integrates with TSN networks. And let's get into it. So synchronization, may it be time or frequency synchronization, is a key enabler for many different applications, supporting deterministic communications with reliability of 10 power minus 6, a latency up to 1 millisecond, as a synchronism with a jitter of 1 microsecond has been the focus of the upcoming 3GPP use cases for the URLLC, that is the ultra-reliable low latency communications. So if we look at cellular networks, we have the requirement, or let's say the desire, for having much faster scheduling. We want to have shorter and faster transmissions. We want to have preemption. All of these mechanisms require very tight synchronization between the UE, that is the user equipment, and the G node B. This synchronization could also be called as the RAN synchronization. On the other hand, if we look at use cases coming from industrial automation, which include collaborative robots or human interacting with robots, working together with robots, these put very critical requirements on the time synchronization, because here time synchronization is not only important for the realization of these use cases, but also for the safety of the humans in the loop. Apart from this, there are also emerging use cases that require positioning to the sub-centimeter level, and their time synchronization accuracy directly translates into the positioning accuracy. Now let's look at some time synchronization basics, because before we talk about different time synchronization protocols or techniques, I think we need to understand the architecture and functionality of a digital clock. A digital clock consists of an oscillator and a counter. The oscillator generates a frequency signal, a continuous signal with a defined frequency to determine the length of a second. And the counter is keeping track of the number of seconds or the clock cycles that have occurred. Now, a clock can use this information to estimate the correct UTC time by adding the elapsed cycles. If you look at real oscillators, they are not really perfect. And they encounter certain imperfections that affect the frequency accuracy and stability. And imperfections can also be temperature gradient, it can be vibrations, it can be oscillator aging that can reduce the precision of a clock. Hence, it is required to regularly synchronize to have a required accuracy. Clock needs to be aligned both in frequency and time domain. Here, frequency domain would mean like that we are trying to align the clock offset, oscillator frequency. And time domain means that we are continuously distributing the time reference. Synchronization begins with a very reliable and accurate time reference source. This could be a very precise atomic clock or could also be a GNSS satellite system. And this time reference is then transmitting its time, and all the other devices are synchronizing or aligning their clocks to this time source. Now let's move to the time synchronization mechanisms in TSN networks. So the TSN standard 822.1as is basically covering the time synchronization aspects in TSN. It specifies a generalized precision time protocol, the GPTP, which is basically a profile of the well-known IEEE 1588 PTP standard with some additional features. GPTP is a packet-based protocol for distribution of timing information, but also for selection of the best clock in the network, which is going to also be the time reference source for the other devices. It includes several performance requirements for different applications. It specifies the best time transmitter clock algorithm. I would like to here mention that I'm using the latest terminology that has been defined by 1588 to make the language more inclusive That means the master has been replaced by a time transmitter and the slave term has been replaced by the time receiver. In GPTB, we also see that it specifies how the timing information is transported within the network. A GPTB network is termed as a time-aware network, and all the nodes or device switches, let it be end stations, are called time-aware systems. It specifies support for multiple time domains. In this figure, you could see that on the left-hand side, we have a domain blue, which is domain number 0. It is synchronized with the GNSS. And on the right-hand side, we have a domain number 1, which is synchronized to an arbitrary clock. And in the middle, the nodes are synchronized to both domains. It also supports external port configuration. I will get into detail of this later, but this was just an introduction. We start now with the best time transmitter clock algorithm. As I mentioned already, this is an algorithm that is used to select a time reference within a network. This was already defined in the standard 1588. Each time transmitter port, each master port, you could call, sends an announce message to its neighboring ports with some clock attributes. Now, the clock attributes that are used by BTCA to reach a decision are mentioned in this table. We have our priority one, which is basically overrides all the other properties. If it's higher, then we go for this clock, and it could also be used to force a manual selection. We have a clock class, which denotes the traceability of the synchronized time of a GM. We have clock accuracy, which denotes, of course, the time accuracy of the time transmitter. We have an offset scale log variance, which categorizes the precision and frequency stability of a time transmitter. And we have a priority 2, which basically, if all the above attributes are the same, would be used. BTCA uses 2 different distinct algorithms to choose a time reference. The first is the dataset comparison algorithm, which the name explains. It compares different datasets that are received at different ports. And the state decision algorithm, which basically defines the port states based on the datasets. BTCA ensures a clear synchronization hierarchy in the network by using a spanning tree to avoid any synchronization loops. Now, when we look at BTCA in practice, we have observed that it introduces certain delays whenever a failure occurs, because it has to put the system in a downtime until a new candidate or a suitable candidate for the grandmaster has been chosen. Apart from this, it is unable to detect only for any transient faults. That means that if GM quality is degrading and coming back up, then we could see a ping pong effect in the choice of the grandmaster. These are the some points to keep in mind. Time synchronization with GPTP. So we talked about how a grandmaster is chosen. Now let's look at how we are transmitting this information in the network, the time in the network. So the GPTP simultaneously accomplishes time and frequency domain synchronization. On the one hand, clock adjusts its frequency offset to match the frequency of the grandmaster. On the other hand, precise time synchronization distributes this time in the network. It is achieved the estimation of different properties. So we have the propagation delay, which accounts for the delay that the message has incurred between 2 adjacent nodes. The neighbor rate ratio, which accounts for the frequency offset between the 2 adjacent clocks. The rate ratio, which accounts for the frequency offset with the grandmaster. We have the residence time, as our colleagues already explained, that this is the time that a packet would spend in a particular time-aware system. And we have the correction field to account for the overall delay message has to incur while traversing the network. Now let's go one by one over how we will do frequency synchronization, how we will do time synchronization. To do the frequency synchronization, we first account for the peer-to-peer delay mechanism. Here, what happens is that in each port that shares a PTP link, so 2 adjacent neighbors, they will conduct this measurement, allowing both to independently account the propagation delay. Let's look at the figure. If we have a peer-to-peer, so the peer-to-peer delay mechanism starts with the initiator sending a P delay request message. As soon as it sends the message, it stores the timestamps T1. It is received at the responder, and it timestamps it with T2. And it responds with the message P delay response, and also timestamp it with T3. Now the responder transmits the timestamp T2 in the P delay response message, and it transmits the timestamp T3 with the P delay response follow-up message. And the initiator also stores the timestamp T4 when it has received the P delay response message. Now the initiator, given these 4 timestamps, can calculate the propagation delay with this equation. That's the first equation. Now this is a very ideal system, considering that the 2 clocks are very accurately synchronized in frequency. In practice, we do not see that. So we have to account for the frequency offset that the 2 clocks have. And that would be achieved by calculating a neighbor rate ratio. Now, if we want to account for the propagation delay relative to the responder time, we have to calculate the rate ratio of the responder to the initiator, which is in this equation, the second equation on this slide. And to calculate then the propagation delay calculation relative to the responder time, we would multiply this rate ratio to the timestamps T4 and T1, because these are the timestamps that were calculated at the initiator having a different clock frequency. That's how we will align the clocks to make sure that the timestamps are actually then in the same time frame. Then how do we distribute the timing information to get the synchronized time throughout the network? The transport of timing information in GPTP is supported by both a 2-step mode, which would have synchronization messages and follow-up messages, or a 1-step mode, which would only have sync messages. If you only have sync messages, then certain timestamps will be created right before the sync message is sent, and then calculations are performed and inserted into the sync message. And let's look at this figure now. Here we have 3 different time-aware systems. The first time-aware system is I-1, which is the grandmaster. In the middle, we have a time-aware system I, which is any middle station. And in the end, we have a time-aware system I+1, which is, let's say, the sync or the slave, which is trying to synchronize. So if we have a sync message that is sent by the grandmaster, it is time-stamped at the grandmaster, and this timestamp, if we have a 2-step mode, is inserted into the follow-up message along with the correction field and the neighbor and the rate ratio. Now the rate ratio here is the rate ratio between the local clock and the grandmaster, which basically, if you look at the equation number 2, is accumulative neighbor rate ratio. To account for the time spent between on any intermediate node, we calculate the residence time, as I mentioned before. This residence time will be calculated here in this figure, for example, using TR and TS at the time-aware system I, which basically accounts for the time spent within this time-aware system I, and this will be then added to the correction field. In this way, we are able to account for the delay. And finally, the synchronized time will be calculated by adding the correction field to the precise origin timestamp. That's how we are then achieving the synchronized time in the network. Now, there are also some additional features that are upcoming in 802 for 802.1as. It's a time synchronization in TSN. So as I mentioned before, there are some drawbacks of using BTCA. And if you are looking at time critical applications, this could be considered as a drawback, where we are in a downtime in terms of time sync, looking for the next grandmaster. So the 802.1as, so the 802.1 working group is basically working on an amendment, 802.1 ASDM, which basically introduces hot standby redundancy, which means that we have 2 grandmasters in the network. One is a primary grandmaster, and the other one is a hot standby grandmaster. The hot standby grandmaster synchronizes itself to the primary grandmaster before it starts sending any synchronization messages in the network. In this way, we have at a time 2 times that are transmitted to the end station, and based on the redundancy, it uses the primary time. If it's not available, then it switches to the hot standby without any loss of time. So the mitigation for any link or a device failure is very predictable and rather also very expected. The ASTM also introduces certain other mechanisms that make the time synchronization reversible. So more reliant. It can merge different time domains into two different time domains into one. It can transmit synchronized time from one time domain to another time domain, and it can also detect sufficient quality of a GPTB domain to be used for a hot standby. So I think that was the end for the TSN time synchronization mechanisms. Now we look at the side what happens when in the middle we replace some of the nodes or the bridges with the 5G system. So as the 5G and TSN come together, there are different distinct time synchronization mechanisms that run in parallel. So if you look at this figure, where in the middle we have the 5G system, we have the G node B, we have the UE on one side, which is the RAN side, and on the core side, we have the UPF. As the 5G integrates with TSN in respect to the time synchronization, the 5G system acts as a time-aware system. That means it's able to support the GPTB protocol. And the functional entities that are at the edge of the 5G system, both the network side, which is the NWTT, and the device side, which is the DSTT, they are able to generate GPTP messages to support the protocol, TSN time synchronization protocol. Now, if we look at the standardization that has been done to support time synchronization in 5G TSN network, already with the release 16, we saw the support for downlink time synchronization. That means that any end station that is on the network side of the 5G system could be a grandmaster, and it could synchronize all the end stations on the device side of the 5G system. How it is achieved, as we saw before, each time the sync message enters the 5G system from the network side, the NWTT timestamp it with the ingress timestamp. And as it goes out of the 5G system, we are able to timestamp at DSTT with the time egress timestamp, and that's how we calculate the residence time to account for the time that's spent in the 5G system. Now, if we look at the overall synchronization in this, the 5G clock synchronizes all the 5G entities, yeah? 5G system. So this means that the UE, DSCT, UPF, NWTT, all of them are synchronized to the 5G time. And when the sync message is transversing from the TSN network over the 5G, we are always given a time error budget. So what we are allowed, or what the 5G system is allowed to add, that is around 900 nanosecond. Yes, please. So in terms of time synchronization, we are looking at, so as I just mentioned, the 5G clock, as here in this setup, is residing at the G node B. It's synchronizing two different clocks, NWTT and DSCT, right? And this synchronization could not, if you remember the mechanism of calculating the residence time, we were doing it at intermediate node, and the time stamping is done by a single clock, the ingress and the egress. Here in the 5G system, we are at two different places, right? The NWTT, which is synchronized via UPF, which is ultimately synchronized by G node B. Of course, there would be very little chance of difference, but still a chance. And then the egress timestamp is done by a different device, which is a DSTT, and that is synchronized over UE, over the G node B. Here, given the dotted line here, the air interface, there is a higher chance for error. So these are the sources of error that we look at when we integrate with 5G for the time sync purposes. But in terms of when it integrates with TSN networks, what is the error budget that we have? That's 900 nanosecond. Nanosecond, yeah, that we are allowed. Now, this budget is divided, of course, between a transport network budget, air interface budget, and a device side budget. And then we can account for which are the greatest sources of error and how to account for them. Of course, there are some mechanisms already introduced by 3GPP to account for packet delay compensation, as we have in the data packets, also for the time sync packets. Yeah. Yeah. Budget, yeah. In DSN or agency? Yes. Only the 5G system would have this budget as a bridge. That's the maximum that's allowed. 60, 82, do you mean? Yes. 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 So this was what we talked about, the downlink synchronization. Now with release 17, we have also seen support for uplink synchronization. That means a grandmaster could also reside on any TSN station that's connected to the device side of the 5G system. And also with timing as a service, that's the 5G feature, which also allows the 5G time to be distributed to the external networks. Here, the 5G TSN AF, this is a TSN application function, allows for exposure of 5G clock attributes to the external network so that it can be used as a BTCA contestant. I think that brings me to the end of my presentation. If you're further interested in the details of time sync for TSN and 5G TSN, then you could look at these standards for the details. And thank you. I thank you all for your time. And if you have any questions, please go ahead.
We have one online question here.
Yes.
Yes. Hello. Can you hear me?
Yes.
Yeah, I had a question about GPTP and TSN. So I was wondering, how does like the PTP messages are sent through in the network periodically, and I was wondering how does this work in relation with a TSN network where your critical traffic runs in certain schedules, and doesn't this affect PTP performance, or I'm not sure how this works.
So as far as I'm aware, they are separately scheduled as
So-
compared to, so it's
Yeah.
not part of any best effort traffic or
So it's like seen as a separate flow between the entities in the
it's
network.
very high priority as far as I remember,
Yeah.
and not part of best effort traffic.
Okay. Yeah. Thanks.
Mm-hmm.
So in TSN, there's also a specific traffic class for example, GPTP, which is part of the network control messages. And there you usually also have some zero jitter requirements, of course.
Does this answer your question?
Yes. Thank you very much.
Any other